Alright, continuing on with part 2 video. Here in this example, we're going to sketch the curve represented by the graphs of x equals f of t and y equals g of t. So what we're going to have to do is we're going to have to kind of create the domain, if you will, for each function. So the one thing I want you to notice about my graphs is now the t is the variable representing the horizontal axis. In the x of t or f of t function, the y variable, or I should say not the y variable, the traditional y axis is now called the x axis. And in y equals g of t, the y axis remains the y. So watch for that so you don't goof up your points. So in both cases here, it appears that t is going to range from -1 to 1. So that's going to be the domain for our t's. And the g of t function has turning points. It appears at, well, if this is -1, we'll say that's about halfway at -1/2, and halfway between 0 and 1 at a +1/2. So this is kind of informing me that I probably want to count by halves. So -1, -1/2, 0, 1/2, 1. So reading my x function at t equals -1, I'm at 0 for the x. And halfway in between, I go up here. That looks maybe, I'm going to say 3/4. It's past the halfway point. It looks like half of the upper half. So we're going to say 3/4 is a good guesstimation. At 0, we're at 1. 1/2, 3/4. And at 1, we're back to 0. So that's the x values from f of t function. Then for g, we started out at -1 for t. We're at 0 for y. Then we're at -1, 0, 1, 0. So that's these points in red. So if we start plotting our points at 0, 0, that's t equals -1. At t equals -1/2, we're going to go to 3/4 -1. That's t equals a -1/2. Again, I apologize for this being a smaller font, but I didn't want to pollute the graph with a bunch of labels. At t equals 0, we're at 1, 0. At t equals 1/2, we're at 3/4, 1. And then at t equals 1, we're back to 0, 0. So 2 labels for the origin. So this is the shape of my curve giving that direction. So looking at what's taking place, for t going from -1 to 0, the x's increase to 1. All right, so my x's are increasing to 1. They're going from here to here, or you can see it in the table. My y's are decreasing to -1, then increase back to 0. So the y values decrease, then they increase back to 0. And you can see that here in the table, 0 down to -1, back to 0. When we go from 0 to 1, now the x values are decreasing. So we're starting here, and my x's are going back to 0. And my y's are increasing to 1, then decrease back to 0. So that's kind of the description of that graph. Okay, two sets, I talked about this earlier, two different sets of parametric equations may have the same graph or portions of the same graph. So for example, 5 and 6, we're going to eliminate the parameter to find the Cartesian or rectangular equation of the curve, sketch the curve, and indicate the direction of the parametric or the parameter as the parameter increases. So in the last video, I told you how two different types of parametric equations can represent the same picture. All right, so here, let's go ahead and turn this into our Cartesian equation. I'm thinking since x equals a cosine theta, y equals sine theta, I'm thinking this is some circle. That's my r factor, so I'm thinking this is a circle centered at the origin with, I believe, a radius of 2. So dividing over the 2, substituting that into our trig identity, x over 2 being squared plus y over 2 being squared. 2 squared gets multiplied to the 1. So, yep, this is my equation of a circle centered at the origin with a radius of 2. So again, my theta, if you go to your calculator, type these in for x, type this in for y, 0, pi over 2, pi, 3 pi over 2, 2 pi. My points when t equals 0, I'm at 2, 0. Pi over 2, we're at 0, 2. At pi, we're at negative 2, 0. 3 pi over 2, we're at 0, negative 2. And 2 pi, we're back to 2, 0. And so there's my circle. There's the direction, and I got all my points labeled. Now, to help you draw a really good circle, if you don't happen to have a compass, take your pencil, put the point at one of the points on the circle on the x or y axis, move your, I'm going to say, thumb and index finger, squeeze it at the origin, then move your pencil maybe 2 or 3 places in each quadrant and just make a little tick mark arc, and that will kind of give you reference points to make a good circle with a radius of 2 on your graph paper. So, we made a circle. Example 6, it's going to be all or part of this circle, but it's a complete different parametric equation. Here we had trig functions with theta as our parameter. Here we have algebraic functions with t as our parameter. All right, well now because it's square root, we have some restrictions. For example, for the square root of t, this t has to be greater than or equal to 0. Here, the square root of 4 minus t, you got to guarantee this to be a positive. So 4 minus t, set that greater than or equal to 0, means 4 is greater than or equal to t, or t is less than or equal to 4. So that tells me my t values have to go from 0 to 4. Now again, to turn this into our Cartesian equation, x equals the square root of t is already isolating the t, but we have to get rid of the square root. So I square both sides. So t is equal to x squared. Substituting that into the y equation, it gives me y equals the square root of 4 minus x squared. Square both sides gives me y squared equals 4 minus x squared. Add the x squared over to the left. Taking my 4, breaking it down to 2 squared, gives me again a radius of 2. So it's the same Cartesian equation. It's just now going to be, where's my starting point, my ending point as I graph this. So again, t, 0, 1, 2, 3, 4. When t is 0, the square root of 0 is 0. The square root of 4 minus 0, which is 4, square root of 4 is 2. That's my first point. I put 1 in for t. The square root of 1 is 1. 4 minus 1 is 3, square root of 3. I put in a 2. Square root of 2, 4 minus 2, square root of 2. Put in a 3, square root of 3. 4 minus 3 is 1, square root of 1 is 1. Put in a 4, square root of 4 is 2. 4 minus 4 is 0, 0. So t equals 0 is at 0, 2. T equals 1 is going to be at 1, the square root of 3, which is approximately, I believe, around 1.7-ish. When t equals 2, I'm at the square root of 2. That's like 1.4, 1.4. And now this point here at 1 square root of 3 is now square root of 3, 1 from t equals 3. So this is going to be kind of like 1.7 to the 1. And then when t equals 4, we're at 2, 0. And there's my curve. This is the direction. And so this parametric equation represents a fourth of my circle. Again, with these domain restrictions on my time, we can only plot a fourth or a quarter of the circle. All right, next, example 7. Find a set of parametric equations. Given that t equals -1 is at the point -2, -7 for the equation y equals 4x plus 1. So when t is equal to -1, I'm down here at -2, -7. Well, we have a slope of 4, so from here, if I go up 4 to the right 1, I'm at -1, 3, so I would say, okay, that's my next point. This is at t equals 0. Do the slope again, up 4, right 1. That's when t is equal to 1. I'm at 0, 1. Use the slope again, up 4, right 1. This is when t is equal to 2. I'm at 1, 5. There's my line. That's the direction in which I'm traveling. If I start with my table, t being -1, 0, 1, and 2, and now I plot all my x's, -2, -1, 0, 1, plot my y coordinates, -7, -3, 1, 5, I can use this table to create my parametric equations. So for my x, I notice that, hey, look, all my x coordinates are 1 less than the t. So x of t is t minus 1. Now for the y coordinates, because we have this slope of 4 over 1, notice that my -7 to -3 increased by 4, increased by 4, increased by 4. So I would use, if you will, my point slope form, or take t minus 1 and put it into my equation for y, put in t minus 1 for x, distribute the 4, and come up with y of t is 4t minus 3. So when t is -1, 4 times -1 is -4 minus 3, I get the -7. So here's one of my parametric equations. Another possible way of doing this is to let x of t equal 2t. So putting in 2t for x, y equals 8t plus 1. So how does this work in creating my table? Well, 2t just means I am going to a bigger jump. So when t is -1, I'm at -2.7. When t is equal to 0, I'm jumping up to 0.1. So that's like doubling my time, is like doubling my original slope. So if I had t equals 3, put that in my table, I would go up 4, right 1, so I would be at the point 2.9. And so this is another parametric set of equations that graph the same line. Okay, last example 8. A projectile is fired with an initial velocity of v sub 0 meters per second at an angle of beta above the horizontal. With no air resistance, then its position after t seconds is given by the parametric equations x equals the initial velocity times cosine beta times t. Y is equal to initial velocity times sine of beta t minus 4.9 t squared. Let beta be 20 degrees and my initial velocity be 300. All right? When will the bullet hit the ground? If it's going to hit the ground, that means our y is equal to 0. Solve that for t. Okay, so let's go to the y equation. 300 in for v sub 0, sine of 20 degrees times t equals 4.9 t squared equals 0. Well, factor out a t. Set each factor equal to 0. Well, t equals 0 is not possible. We haven't fired the gun at t equals 0, so it hasn't hit the ground yet. Take 300 sine of 20 minus 4.9t, set that equal to 0. Okay, add over the 4.9t, divide over the 4.9. There is my exact value. Go to your calculator, type it in. Just make sure that when you type this in, your mode is in degrees. So I would have to change this. Go to your mode, change my radians to degrees. So alpha y equals a fraction. And then I can type everything in. So 300 sine, I believe it was sine, right? Yep, sine of 20 divided by 4.9. Yikes, what did I do here? I apologize for that. 4.9, you go down there. There we go. 20.94. So approximately 20.9 seconds. Now, the other thing you might choose to do, because I'm guessing we may have to use that time again, for example, part B here, how far from the gun will the bullet hit the ground? Okay, so we found the time at which it hit the ground. I'm going to go back to my calculator, store this for whatever variable you want. Let's say t, because we're in the parametric and that's what it was. It's saved. Now take your x equation, 300 for the velocity times cosine of 20 times the t. That's this fraction right here that I saved in my calculator. So I'm going to go in my calculator, 300 cosine of 20, and then times t. So 5,903 meters. Oops, got stuck there in between monitors. There we go. So if we round that to the nearest meter, that's where we're at. What was the maximum height reached by the bullet? Okay, well, take the y function. If we take the derivative of that function, y prime, set it equal to 0, that's when you find the horizontal tangent. So the path of my bullet or projectile is going to reach a maximum height and then come back down. So y prime, that will be 300 times sine of 20. The derivative of t cancels to a 1, so that's this. And then minus, bring the 2 times 4.9 is 9.8t. Set it equal to 0. Solve it. Type it into your calculator, approximately 10.47 seconds. Now, what's my maximum height? Take this value again. You might want to store it for t, and we type it into our y equation. 300 sine of 20 degrees times 300 sine of 20 degrees over 9.8 minus 4.9 sine of, 300 times sine of 20 degrees over 9.8 squared. So it might be beneficial to have this in your calculator stored, so you just have to go 300 sine of 20 times t minus 4.9 t squared. Gives us approximately 537 meters. And that wraps up our 10.1.